Hi everybody, Mr. D here, checking in from Math Muscle. This particular video will use calculus to sketch functions, in this case here a third degree function, a cubic, by completing certain steps. For example, part one is determining the x-intercepts, the roots, and the y-intercepts. Step two is using the first derivative to find intervals of increase and decrease using a sign diagram, and finding the corresponding coordinates of local max and local min values and points. Using the second derivative, we're going to apply a test for concavity, a sign diagram test similar to that of the first derivative, and then we're going to state the coordinates of the, if any, points of inflection, and lastly, use that information from the above three steps to sketch a well-labeled diagram of this particular function. So, moving along. Part one, looking to find the x-intercepts, also known as the roots of the particular function given. So in this case here, for the x-intercepts, we're setting y equal to 0 as is customary, and using the factor theorem, which is present from advanced functions. Those of you that are Ontario students will recall that the advanced functions is a pre or co-requisite to calculus and vectors. So here we go. We're going to try any factor of -2 and sub it into the original function to see if we get a value of 0. So we try the easiest one, which is 1. When we substitute it into the x values, we get a value other than 0, so that cannot be an x-intercept. Try -1, which is the next easiest one to select. That's a factor of -2. And upon doing so, we get an answer of 0. So we know that there is an x-intercept at x equals -1, which makes x plus 1 a factor. That's one factor. We're going to have to go about using polynomial long division for the other factor. And again, this is from advanced functions. I've gone ahead and done that. I've also posted a video using polynomial long division on Math Muscle, my YouTube channel. So if you want to sort of get some background on how this process works, please go and look at that video. So here you are. It provides this trinomial. Oops, and I just forgot an exponent of 2 there. I just noticed that. So let's just insert that there. So this is 4x squared plus 7x minus 2 times this original factor of x plus 1, and that equals the original function given. But then we have to factor this, and again, I have a video that's a subset of the polynomial long division video. It's all included that shows you how to handle factoring a quadratic. So please look at that video should you need to. And then we get to set y equals 0, and we get x equals -1, x equals 1/4, and then x equals -2. So those are our x-intercepts. Our y-intercepts aren't quite as involved. We basically have to set x equal to 0, and in doing so, we get y equal -2 in our original function, which is basically this constant value. So those are pretty important values that'll help us guide our sketch. Part 2 is asking us for when is the original function increasing, going upwards, or decreasing, going downwards. So we use the first derivative and set it equals to 0 to come up with those critical numbers. So in doing so, we take the first derivative of the original function, and we get that quadratic. You can try to factor that or use the quadratic formula. I'm not sure it's factorable when I did that, so I just used the quadratic formula. And using the quadratic formula from prior learning and careful substitution, with our a being the coefficient of the x squared term, b being the coefficient of the x term, and c being the constant. Using some calculator carefully, again with the signs, you have to make sure that you're doing this carefully, you should come up with 2 values. Those are critical numbers. The question is, where in between those critical numbers or outside of those critical numbers is the original function increasing or decreasing? So we can use a sign diagram for the first derivative. And the first derivative sign diagram, basically what that does, it's a horizontal line that has these particular values placed on them. That's how it all starts. Then what you do is you select test points in each of these three regions. And in doing so, you just pick basically any integer value, and you substitute that value. So for example, in the center here between these two critical numbers, I picked -1. To the right of 0.266, I picked 0. I mean, let's pick the easiest values. And to the left of -1.57, I picked -2. You take those test points and substitute them into the first derivative. And that'll tell you the behavior of the first derivative. All you need is the sign of the term. In other words, whether it's positive, whether it's negative. So in this case here, we have a positive value, right? So at the test point of -2, we have positive values, as well as at the test point of 0, we have positive values by virtue of at x equals 0, we come up with a value of 5 in our first derivative. And remember, our first derivative was given above here. So we're substituting our test points not in the original function. That's an important thing to differentiate. We're not substituting into the original function. This is a sign diagram for the behavior of the first derivative, and then that will tell us how the original function is behaving. And then we have at -1 test point in the derivative function, we get -5, which is less than 0. So what does that tell us? Well, it tells us that the original function is increasing in the yellow regions, and in the blue region here, it's decreasing. So the interval of increase is from -infinity to -1.57. So that's an interval of increase, as well as between -0.266 and +infinity. In that region, it's also increasing. And in this blue region in between, the function, the original function, is going downward. So that's an interval of decrease. So all we need next is to determine where is there a local maximum and where is there a local minimum. Well, you can see how the function will go up and then down, which implies at -1.57 we'll have a local maximum. And then the function decreases, and then at -0.266 it begins to increase again. So therefore it seems logical to assume that there's a local minimum there, and I've done my best to try to indicate that that's the case by using these arrows. And now all we need are the y coordinates for those x values, and you substitute those x values into the original function now, because keep in mind we want to sketch the original function, which is this cubic. Once you've substituted those values in and using your calculator very carefully, using brackets and keeping in mind these are negative values for x, you should come up with these two coordinates for local max and local min respectively. If you like, you can pause the video right now and try to check your dexterity on your calculator to see if in fact you can reinforce that these are in fact the corresponding y coordinates. So go ahead and pause the video and try that out, and then resume it as we move on. So now we're asked to find intervals of concavity. So similar to the intervals of increase and decrease, where we set the first derivative equals 0, to determine concavity, in other words, where the function changes from a frowny face to a smiley face, or from a smiley face to a frowny face, we have to find where the second derivative equals 0, because at some point the concavity changes. So we take the second derivative, which means the derivative of the first derivative, and we get 24x plus 20, set that equal to 0, and we get x equals -0.917. A quick note here that what I did was I'm using y and f to represent the function interchangeably. And you should get comfortable seeing a derivative or a second derivative in this case as y prime prime and f prime prime, because those are commonly used notations. So moving along, do the second derivative sign diagram, pick a test point to the left of 0.917 negative and to the right of 0.917 negative, and substitute now into the second derivative to see whether or not it's positive or negative. So in this case here, let's have a quick look. When we substitute a test point of -1 into the second derivative, what do we get? We get a negative, which corresponds to the original function being concave down. When it's positive, when our test point is positive in the second derivative, we have what's called concave up in those corresponding intervals. So there are your intervals of concavity. So concave up and concave down in those particular intervals. And then let's come up with the y coordinate by substituting into the original function. And my conclusion is, resulting from this sign diagram, we have a change in concavity at that x-coordinate. So therefore, it can be said that at that particular x-coordinate, there's a point of inflection due to the change in concavity. So now we have another special coordinate here that will help us out when sketching. So moving ahead, now we take the local max, our local min, our change in concavity location here, which probably should be labeled. So I'll just take a quick snapshot of that particular coordinate. We'll paste that in there. Oh, what happened there? Let's try that again, shall we? Take a screen grab of that. So that's where the concavity changes from a frowny face to a smiley face. In other words, concave down to concave up. We have our y-intercept at 0, -2. We have our 3 x-intercepts, and we label the original functions. We probably should label the axes x and y as well. So I'll do that, but at this point, I think I'm going to sign off and say thank you for watching. If you're not a subscriber, please subscribe to the Math Muscle YouTube channel. And if you have any questions or comments, please include them below. Share this with your friend if you feel like they'd benefit from it. Thank you.